Just how linear momentum is P equals mv. Angular momentum equals inertia, which is like the rotational equivalent of mass, and angular velocity. This is the standard equation for angular momentum. Linear momentum tells you how hard it is to stop something in motion. Angular momentum tells you how hard it is to stop something from rotating. It's why planets keep spinning. It's why gyroscopes can stabilize spacecraft. First of all, momentum is always conserved inside a closed system. So the initial angular momentum value is equal to the amount of angular momentum at the end. And this only holds true if no external torque is applied. Just like how linear momentum is also conserved, but only if no external force is applied. So angular momentum in total stays the exact same no matter what's spinning. Have you ever seen ice skaters? If you've ever seen an ice skater spinning around in a circle like this, and they slowly pull their arms in, and they magically speed up by a lot, even though their mass is the same, they didn't really kick off anything, they just brought their arms in closer, and they suddenly rotate way faster. Why? Because angular momentum is conserved. When their arms are out, there's a higher distribution of mass from the axis, which means that the moment of inertia is larger, and the angular velocity is pretty low compared to when they bring their arms in. That's because angular momentum is equal to IW. To keep the value the same, because it's supposed to be equal, the same, inertia goes down because the mass gets closer to the axis. This is assuming no net torque is applied from the outside, so no one's pushing them. All they're doing, they bring their arms closer, therefore lowering the moment of inertia and raising the angular velocity. And in total, angular momentum is the same before and after. Imagine you're in a physics lab and you're a scientist and you have two steel discs that spin freely on a vertical axle. Let me draw this out for you. Here's our diagram. So you have two steel discs and A is at rest. So angular momentum is 0. B, however, is already spinning. What you're trying to do in this physics lab is you're trying to lower disk A on top of disk B. They lock together and they spin as one object. And what we're trying to find is the final angular velocity after they merge. Let's give some values. The mass of B is 5 kilos. The radius of B is 0.3 meters. And the angular velocity of B is 10 radians per second. Let's look at A, which is at rest. So the mass of A, 3 kilos, is a little bit lighter. The radius of A is 0.3 meters. It's the same size. And the angular velocity of A is 0. What is the final angular velocity? So we know that momentum is conserved. That means initial angular momentum is equal to final angular momentum. Each of these are a solid cylinder. Let's find the moment of inertia. And if you forgot the formula, go get the free cheat sheet in the description. Anyway, the moment of inertia for this kind of shape, what shape is that? That is a solid cylinder. So the formula is 1/2 mass radius squared. Let's break this into steps. First step, we'll find initial momentum. Second step, we'll find the total final momentum. So the total angular momentum before, the only thing moving here is disk B on the bottom. So it would be the momentum of B. And if you're wondering where we got this from, remember, L equals I angular velocity. And we're not going to consider disk A because it's at rest. There's no momentum there. If we go and plug in this value for I, we get 1/2 mass of B radius squared multiplied by the velocity of B. Okay, cool. So we found the initial amount of angular momentum. Now we have to find the final momentum. After they lock together, the masses combine. So we would write it as the inertia of B plus the inertia of A multiplied by the final angular velocity. We consider their inertia as one object because they lock onto each other. Now, let's set up our equation so they're equal to each other. So we can write initial momentum equals final momentum, this. And all we've done here is I've expanded the moment of inertia into the cylinder expression. This looks very cluttered and you might be a little bit lost, but there's something we can cancel out here to clean up like half the equation. We can cancel out radius squared and 1/2 because it's everywhere in this equation. So that's all gone. What we're left with is this equation. Mass of B times velocity of B equals mass of B plus mass of A times the final velocity. All we have to do is find this. So let's divide this onto the other side, angular velocity, for this answer here. Okay, cool. We have our equation. Now we're ready to plug in our stuff. And remember, it's always easier if you rearrange variables first before putting in numbers. Don't get all happy and plug in your numbers when the equation is halfway through. There's a higher chance you'll make mistakes. Look how clean and easy this is. We have our answer right on one side. So plugging everything in, 5 times 10 divided by 3 plus 5. 50 divided by 8, it's equal to 6.25 radians per second. That's how fast our discs are spinning after they lock on. Let's look at what this means. Okay, look at this number, 6.25. The initial speed was A was at rest and B was spinning at 10 radians per second. When they lock onto each other, A starts spinning, but because angular momentum is always conserved, we have to steal some of this speed from disk number B to put it into disk A to get that spinning as well. That's why the velocity in total goes down. For every topic I cover, I like to create a free cheat sheet, and I use them myself as well. So if you want your own with all the formulas you'll ever need in one place, then go sign up in the description.